All right. Welcome to today's Corundum developer meeting. Thank you everybody for taking the time to tune in today. Let's see, we got a couple of things. I'm going to go over a couple quick announcements and then go through some status updates on Corundum. All right, so announcements. Next Corundum developer meeting will be April 24th as scheduled. Figured I would go ahead and put this up on a slide so that everybody's aware of it. Let's see, the next Switch development meeting will be on May 1st. Normally the next one would be, in 1 week on April 17th, but I have jury duty, so we're going to skip a week. Yeah, I guess potentially we could have another one, on a different day, but we'll have to discuss that, next week sometime. And then I'll post on Zulip if there's any changes with regards to that. All right. So getting into the status update summary, a couple of things to take a look at here. We got the FIFO memory inference bug. We got the AXI virtual FIFO, which at this point is pretty much done. Then over the past week, I've been doing a bunch of work on the some of the queue management components in Corundum. I did a bunch of work on performance, trying to remove all the MMIO reads from the fast path. That's done. I also implemented an indirection table in Corundum as part of the queue selection on RX. That's done. Well, almost. I need to get it committed, but it's working in the hardware. And then I've also been doing some basically brainstorming on kind of longer term what the what sort of changes I need to make to the queue management logic to as part of the implementation of some of the improved descriptor fetch and completion write back support and a few other things. So I'm going to go touch on some of what I've been looking at for that. All right. So, I've made some changes to the queue management logic, but I've tried to keep things kind of as backwards compatible as possible. But at some point, we're going to have to do some significant reorganizing, and that's what I'm going to touch on. All right. So the FIFO memory inference bug, I guess there's not much to say about this one. I don't see any of the folks on from MLE on at the moment, so I can't ask them if there's any status updates if they're not on the call. Yeah, so this one's been reported to Intel. I'm probably going to end up testing this myself effectively in the next couple of weeks because we're starting to get things spun up on the Intel FPGA side of things again. So yeah, no updates on that for the time being, but we'll circle back to that hopefully pretty soon. Okay, so moving on, the AXI virtual FIFO. This one is basically done at this point. It's been committed to the Verilog AXI repository, and that code has been pulled back into the Corundum repository. So it works at the 100 gig line rate. Everything seems to be pretty stable, although it has not been super extensively tested yet. I guess we'll have to see. But it's certainly ready for people to start hammering on it. The DMA benchmark designs in Corundum itself have also been updated to use the AXI virtual FIFO component as part of the DRAM test. So that's been set up for most boards that have DRAM, at least for UltraScale Plus, to make sure that the memory interfaces are actually working from the standpoint of the application section, that everything's accessible and whatnot. All right, so a little bit more detail on the DRAM benchmarking design. So that's been updated to include the DRAM channels, and ostensibly it should work on any board, but some of the boards don't have the memory interfaces set up yet. So I don't think I've done this for any of the Intel boards yet. And I think most of the Intel boards are going to need some sort of AXI to Avalon conversion in there somewhere. And then also 7 series parts don't have the MIGs configured either because the process is somewhat more complicated than for the UltraScale parts. And I just haven't had the time to sit down and make it work. Now for the DRAM channel test in the benchmark, this doesn't use actually the full AXI virtual FIFO because that one is designed to use multiple internal memory channels. So you can take, one, relatively wide AXI stream interface. You can take in packetized data, and then that gets encoded and striped across multiple internal FIFO channels. So there's encode and decode logic and striping and destriping. There's a bunch of additional complexity associated with that. But in this case, we just want to test the individual DRAM channels independently and make sure everything, looks reasonable. So we don't actually need all the encode and decode logic, because what we can do is just take kind of the core FIFO channel module from the virtual FIFO and connect PRBS generators and PRBS checkers to that. So that's how the benchmark is set up. It's pretty straightforward setup. And I guess I should also say that this is also operational for HBM on the Xilinx parts that support HBM. I haven't done anything with Intel HBM yet, but presumably it'll be pretty straightforward to make it working, or to make it work on there. So yeah, this at least this core channel module does close timing at 450 megahertz on like the U50. So that's pretty good. I think also the U50 design has 16 instances. I don't think I was able to get close timing with 32, but I dropped it down to 16, so it's using half of the HBM channels, and it works. Potentially you could use all of them with some more careful placement. All right, moving on to the MMIO read removal, which people are probably going to be a little more interested in. So this is something that I've had a few people ask about here and there, something that I've been meaning to get around to working on for a while. Previously, I had looked at basically doing Q pointer write back, where we have where instead of reading the Q pointers from the driver via MMIO, we would have the hardware just write those out somewhere in host memory. And I'd spent some time a few months ago, working on an implementation of that, and was running into some performance related issues that my hypothesis is that it was coming from not having interrupt coalescing enabled, but I'm not sure if that was necessarily correct. There might have been something else going on. But anyway, for MMIO read removal, just kind of a high level of what the point of this is. Queues are used to transfer descriptors from software to hardware and completions and events from hardware to software. And every single one of these queues has producer and consumer pointers. And these pointers have to be synchronized in some way between software and hardware. They don't always have to know exactly what the queue values are, but you have to have a way of making sure that these are transferred such that the queue operates correctly. So currently this is done via MMIO. Actually, I guess one of the things I should mention is that the actual queue itself, the ring buffer, lives in host memory. So the host has direct access to it, but the hardware has to access it via DMA. So currently these queue pointer synchronization operations are done via MMIO. So in this case, software can read and write the queue pointers from the hardware with MMIO. So MMIO writes are quite fast, right? Because the CPU will issue the write, and then it doesn't have to wait for it to actually finish, right? It kicks it off, and then it just keeps running, and that write will eventually make its way to the hardware. But on the flip side, MMIO reads are quite slow because the CPU has to wait for the read to complete. So it'll kick off the read request. That'll go out over PCIe. It'll hit the FPGA. It'll process it. The response will come back. Once it's processed by the CPU, then it can continue executing. So actually, I'm not sure what the CPU does during this time. I'm guessing this is where hyperthreading comes in, and the other hyperthread will, make progress while the first one is blocked, waiting for the read to come back. Either way, not so great. So eliminating MMIO reads from the fast path should help improve performance. And there's a couple different queue types here, right? We have the TX and RX queues that transfer information from software to hardware, and we have the completion event queues that transfer information from hardware back to software. So we'll take a look at these separately. For the TX and RX queues, I came to the realization that every descriptor in the TX and RX queues, this results in a completion record after the operation finishes. And as a result, the actual TX-RX queue consumer pointer is actually not really relevant. Hardware owns the packet not until the pointer is updated, but until the completion record is actually generated and received by the software. So in some sense, there's actually no real reason that you would ever need to read the consumer pointer from hardware for the TX and RX queues. Instead, we can just look at the completion queues. When we get a completion, then we can go free the resources associated with that packet and do the cleanup and whatnot. And the implementation of this actually does not require any hardware changes whatsoever. It's just a handful of lines in the driver that have to be tweaked. So this, I've gone ahead and implemented it, and it works, and it's that change is in the development repository already. So that's great. Interestingly, I did not see a huge difference in the iPerf throughput after implementing this, indicating that if there is a performance bottleneck that we're running into in the hardware or whatever, it's something other than the MMIO operations. But we also didn't see drop in performance, so that's a good thing. Let's see. So moving on to the other queue type, with the completion queues and event queues, the method here is a little bit more subtle. Let's see. In software, we need to know about which records in the completion and event queues are ready for processing. So do we really need to know the exact pointer value for that? Not necessarily. Obviously, reading the consumer pointers is one method. And previously, I was looking at some sort of write-back technique where the hardware could just push the updated queue pointers back to host memory where software could just read it. But is knowing the actual value necessary? Is there some other way of encoding this information into the completion such that software can just look at the completion and go, oh, this one is ready for processing? Well, over the past couple of weeks, I took a look at some existing device drivers and ended up also taking a look at like the InfiniBand spec and the NVMe spec. And the NVMe spec talks about this phase tag bit, and other drivers use this ownership bit. Now, I'd previously seen the ownership bit thing, but it's kind of hard to tell exactly how stuff works from looking at the source code. So I'd seen that, but didn't really fully understand how it worked. But then when I took a look at the NVMe spec with the phase tag, everything suddenly made sense. I'll talk about that in a little bit more detail in a minute. But the idea here is that hardware will set this bit to a particular value, and it does that at the same time it writes out the full completion or event record. Software can simply look at these bits and process while it sees the correct value. As soon as it sees the wrong value, then it's like, okay, hardware has not written the new completion yet, so I'm going to stop processing. And with this setup, we don't need to read the queue pointers at all because we can just look at the completion records. So we don't need to read the pointers via MMIO, and we don't need to have hardware write them out somewhere, because it's just encoded into the completion itself. So a little bit more details on the phase tag bit. The idea is that it's just a bit in the completion that indicates to software that the completion is ready to be processed. And you generally want to put it, I think, at the end of the completion, such that if the completion write is broken into a couple of PCIe, writes, the last one will contain the phase tag bit. So how does it work? Well, the idea is that initially, software will memset the entire ring buffer to 0. So all the phase tag bits will be 0. Then the first pass through, as hardware writes completions into the ring buffer, hardware will set the phase tag bit on those completions. So software can just start from the top, and it will work as long as it sees phase tag bits that are set. As soon as it sees ones that's 0, then it's like, okay, that's as far as the hardware has gotten. And it'll stop processing. Second pass through, once hardware reaches the end of the ring buffer, it'll then start from the top again. It'll write completions with the phase tag bit set to 0. And then again, when software wraps, then it's going to be looking for a phase tag bit set to 0 instead of 1. And with the setup, you can just, keep going through the queue and handling completions without having to actually know what the pointer is from hardware. So this is great because it's relatively simple to implement in hardware. We only need one bit in the completion record, and we don't require any additional PCIe overheads at all, right? We're not doing any MMIO reads. We're not doing any additional DMA operations. So yeah, I went ahead and implemented this in Corundum, and it works great. I haven't tested it on a bunch of different boards yet. Ostensibly the whole point of Corundum is that you should get the same result, or nominally the same result on everything. So I need to do some testing on, some Intel hardware just to make sure everything looks good. But This has been committed to my development repository as well. If people want to start hammering on it, that would be great. Now, I guess one thing I should mention as well is that I did a little bit of kind of sanity checking just to make sure that this test or this change actually took effect, and that I say wasn't running an old version of the code or something. And to do this, I just basically ran the standard MQNIC test script that I put together a while ago, which runs a bunch of different iPerf tests and also PTP time sync in parallel, and just make sure that everything is all the data is flowing the way it should. So let's see. And then what I did is I looked at the statistics counters, and there's not much that's reported in there right now, aside from PCIe related statistics. And well, that's exactly what we need for this. So let's see, I ran 3 different tests. One of them, that's kind of the baseline of how things were previously with all of the pointers read via MMIO. And then I implemented the first part, which is just a driver change where we have the TX and RX queues where we're not reading those pointers and we're just advancing those based on the completion records. And we're only reading the completion event queues via MMIO. And then the third test, everything's read via MMIO. So with the first pass, kind of the baseline, we get about 1.7 billion memory read requests throughout the entire test, and about 2.7 billion memory write requests. So one thing I will say is that these numbers do vary a bit for various reasons. So you can't really directly compare them between tests, but if you take the ratio, I think that's a reasonably good proxy for, the improvement. So if you take the ratio of these two, you get about 0.63, which the memory reads over the memory writes. Now, after implementing the first change, where the TX and RX queues are advanced based on completions, and we're only reading the CQ and EQ pointers via MMIO, we get about 1.4 billion memory reads and about 3 billion memory writes, for a ratio of about 0.47. So definite improvement. We definitely removed some of them, but there's still quite a few reads. So the last test is, full up with everything implemented, with no pointers, hopefully read via MMIO in the fast path. We get about 201,000 memory reads and 3.3 billion memory writes. If you take the ratio, it's a pretty small number. And the other funny thing is, I think a good portion of that 200K memory reads is actually coming from the register dump run that takes place at the end of the test, which provides these statistics counters. So I'm not sure exactly how many reads that is, but it could be like half of that 200K is just the this script reading out all of the registers. So that makes the result even better. But the interesting thing is that the performance results are largely similar when looking at the performance of iPerf itself. So that indicates that the current tests are limited by something other than MMIO reads, either some other component in the hardware, like the descriptor fetch components, or potentially something else in the network stack itself, like all the mapping and unmapping and allocation and whatnot. So I'm not sure about that. That's going to require some further investigation. But the important thing is that we didn't see a drop in performance, which is what I saw the first time I tried the Q pointer write back stuff the last time around. So that's good news. So yeah, like I said, these updates have been committed and pushed up to my development repository. I'm going to do some more testing over the next week, hopefully, and get this merged back into the main Corundum repository where everybody can start banging on it. So yeah, I'll definitely let you guys know when I pull the trigger on that. All right, then the next thing that I took a crack at, actually just over the weekend, is implementing an indirection table. This is something that I've thought about before, but haven't really had a good reason to do it. But with some of the changes that I'm thinking about making to the queue management logic, which we'll get to in a couple of minutes here, we need to support potentially dynamic queue allocation. So the way Corundum currently works, the RX queues at least have to be allocated basically in power of 2 blocks sequentially for RSS to work correctly. But if you're doing dynamic allocation, that might not be the case, right? So you have to have some kind of remapping layer, if you will, that can deal with that. And that's the idea with the indirection table is you can allocate queues however you like, and then you can just load into the indirection table, which queues you want to use. And the entries in the indirection table can be, a nice power of 2 size block that's sequential, and everything works out nicely. So the idea with the indirection table is this replaces the per port offset in the queue selection logic. So with the queue selection logic, I had offset value that would allow you to use multiple ports on one interface and actually have the data from each port end up in a different set of queues. So with the indirection table, the idea is we have an indirection table for each port. So we don't need that offset anymore because you can just bake that into what you load into the table. So the table that you look at is selected via the TID value. The entry in the table is selected via a combination of the application provided tdest and the RSS hash. The default table size 256 entries. That's configurable via parameters. And the application supplied tdest has also been extended with an additional bit. And if you set that bit, and there's also a control register that's associated with that as well, if that's also set correctly, then that particular value will bypass the queue selection logic and will just be used directly to pick the destination queue. So this allows applications, if you want to write to specific queues, you can do that. And the status of this is that it's basically done. I've tested it on the hardware, updated the driver, everything looks good so far. I need to make a few additional changes to the repository to get all of the loose ends tied off, and hopefully I'll be able to get that pushed up in the next day or two. And then I got to test it on a couple of the boards just to make sure everything looks good. But yeah, this looks pretty straightforward. I guess the other thing I should mention as well about the indirection table is that I think it only takes up like 1 or 2 block RAMs. So the footprint of this is quite reasonable. Let's see. So now moving on to some of the changes that I'm thinking about making to the queue management logic that kind of prompted at least this change to the this implementation of the indirection table. So to support improved descriptor and completion management logic and potentially some other features, there's a few things that need to be changed in terms of the queue management logic. And one of the things that I want to do is get rid of sharing between the descriptor fetch completion write logic across multiple queue types. So like the descriptor fetch, I just want to have one queue type basically that's associated with that. For completion writes, one queue type. Event writes, one queue type. So instead of having 5 queue types, right? TX queues, RX queues, TX completion queues, RX completion queues, and event queues. We're going to compress that down to 3 queue types: queue pairs, completion queues, and event queues. And we're going to set things up to support the dynamic allocation of queues. So for the TX side, that's pretty straightforward. I don't think we really need to jump through any hoops there. It's just a matter of, making sure the schedulers are configured correctly and whatnot. But on the RX side, we have to have the indirection table for RSS to work correctly. The other thing I'm thinking about doing is separating the completion and event write logic. So one of the things I was toying around with is combining the completion and the event queues, and having a bit indicating, is this a completion queue or is this an event queue? But doing that introduces the potential for a couple of issues. So I think it makes more sense to keep those separate. And part of that has to do with the logic that I put together a while ago and now need to resurrect for improved completion write back, where for completion queues, you want to support, batched writes where you can basically spool a bunch of completions inside of the write back logic. Once you have a sufficiently large block that you can write all that at once over PCIe. And then you can also defer event generation, which is, basically the proper way of doing interrupt coalescing. But in this case, it's not interrupts directly, it's the events, which then will go on to generate an interrupt. The other component of this as well is that for the events, we don't want events to evict completions from the little write back buffer. That's going to affect performance. And we also potentially don't want to do 2 rounds of interrupt coalescing, you want to do the interrupt coalescing basically with the completions, and then with the events, maybe you just want to fire off the interrupts immediately. So by separating the write back logic for completions and events, that's hopefully going to result in better performance. And also the event write back module can be much simpler than the completion write back module, because we're only talking about, one event per queue basically, whereas the completion write back is going to be, much more throughput, much more traffic, because every single packet gets a completion potentially. So as part of this, we need to think about how stuff is stored on the FPGA. What state do we need? What needs to be exposed in the register space? And what does the FPGA need to keep track of? So with the current setup, this is, I think I've showed this slide a while ago. We're using about 128 bits per queue to store all of the associated queue state for all of the different queue types. And the nice thing about this is we can store this across, we can store this in URAMs. It takes 2 URAMs for 4096 queues. So that's pretty efficient. With the new setup, we're making a few changes here. And the idea, so originally I was thinking about, keeping the RX and TX queues separate, but if we do queue pairs, and the idea is that we can actually amortize this big base address field by just doubling up all the pointer values, which end up being a lot smaller. So previously, one queue requires 128 bits, and with queue pairs, we can put 2 queues in 187 bits basically, which fits into 192, which is 3 URAMs with a couple of additional bits to spare. So this is not necessarily completely finalized, but the idea here is I think kind of clear. We're not getting 2 for the price of 1, but it's more like buy 1 get 1 half off, if you will. So we can use 3 URAMs for 4096 queue pairs, which I think is going to be a pretty significant bump to performance and flexibility over what we have now. And the other thing with the queue pairs is that I guess you don't necessarily have to allocate the whole queue pair. You could allocate just, the TX side or the RX side, which could potentially be more useful for Ethernet stuff. But I guess the other thing with queue pairs is that that's kind of the abstraction that RDMA needs. So if we're going to support RDMA at some point, it makes sense to support queue pairs. The other thing, right, so the way that this sharing the base address field works is that the send and receive rings inside of the queue pair will share the same memory block, the same allocation, which is how you can amortize this register here. So previously, every single queue could have its own, block of backing memory in host memory somewhere. But the flip side about that is then software or the hardware has to keep track of all of these base addresses. But for the queue pair, if you can allocate that together out of a single buffer, allocate one block, cut it in half. We're going to use half for the send queue, half for the receive queue. Then this means we don't need to keep track of as many pointers, as many pieces of memory. So there's a couple other changes that are notable here. I've added an LSO offset field here. The idea with that is to support things like TSO in the transmit direction, where one descriptor could correspond to multiple packets. And then there's also a VF index field here that's going to be necessary for things like SRIOV, such that we can make sure things are associated with the correct virtual function. So yeah, that's how things are looking for the new queue state storage setup. Another thing I've also been looking at is the queue control registers themselves, making some adjustments to that. Several things I'm thinking about. So one of them is potentially placing the pointers in the same D word. And with this, the idea is that it'll take up less space and it can be read atomically for accurate queue depths. Now that we've, and this is more for, the MQNIC dump utility. When you run that previously, since it reads the producer and consumer pointers separately, the queue depths are not necessarily going to be particularly accurate, and you could see some weird stuff. But by placing the pointers in the same D word, it means that, a single read will get you both. And that's, an atomic operation. So you actually have an accurate picture of what's going on. And the other thing I'm thinking about doing is switching over to read-only registers plus written commands instead of kind of the standard scheme of how register spaces work, where you have particular bits defined for particular operations. The problem with kind of a traditional register space, so you might need to perform read, modify, write operations if you want to set or clear a single bit or part of a larger register. So if instead we're doing, some sort of a, encoded command where we have, the upper bits indicating what the operation is, which could be to set or clear a particular bit or write a value into a certain field, and then the low order bits could potentially be the an immediate value, basically. This allows you to do the same thing, right? Because you can modify all the fields you need to, but it's atomic because we're not doing read, modify, writes, and it's potentially faster because, again, we're not doing read, modify, writes. So you don't need to wait for the read to come back. And also you can potentially support multiple operations at once. So for example, a common thing to do with the completion queues is to write the new consumer pointer and at the same time to rearm the completion queue to generate an event. Or similarly for the event queues to do the same thing to write the new consumer pointer, but also rearm the event queue to generate an interrupt. So by using this kind of encoded command, then you can support doing, multiple things at the same time. The other thing that I've been thinking about a little bit is, maybe it makes sense to use some sort of a softcore kind of on the configuration path. Most of the NIC drivers I took a look at seem to use some sort of a command queue, and allocating a queue involves writing out some sort of a descriptor, basically, and queuing that into a command queue and then waiting for the result, or using some other kind of mailbox communication for talking to some management controller on the NIC. And this means that all of the queue allocation can be managed by hardware instead of managing that by software. Now, it's like if you only have one driver connected to the hardware, maybe this isn't necessary. But if you start thinking about, okay, well, how do we make this work with SRIOV? Maybe putting hardware in charge of the queue management is going to make more sense, because then you need less communication between like the virtual function by the guest operating systems on the virtual functions and the host operating system on the physical function. And potentially could also help with the hardware and driver versioning, because with this setup, you can have somewhat, independent data structures that get enqueued to make these different requests, and then the core will just carry out the necessary operation. So you can reorganize, move around registers, change exactly what needs to be done for various operations in the hardware, and the soft core would take care of the details. So I've only started thinking about this, haven't gotten too far down this path, but could potentially be an interesting option to consider. Even things like NVMe, I believe, do queue allocation and whatnot in this way. Anyway, that's about all I got for today. So if you guys have any questions or comments, go ahead and fire away. I guess, like I said, all of the updates for the MMIO read removal and whatnot, that's going to be made available in the main repository, hopefully in the next week or two. I just got to do some cleanup on the indirection table stuff, and then do a little bit of testing and get all those things pushed over once I'm confident things are working as expected. But as of right now, if anybody wants to try this stuff out before it hits the main repository, I've been committing stuff to the UCSD sysnet fork of Corundum.
Yeah, thanks for your help getting that working this weekend. So I've got the 250 and the U200 built.
Oh, very nice. Right. And that was with the DMA benchmarking design, right? So that includes memory channels.
Yeah, funny, if you follow the instructions, it works much better.
Yeah, sometimes the make build can be a little finicky, so it's good that that we made everything work. Sometimes you just got to do a make, clean, and make to make sure that it gets everything. All right. Anybody else have any questions or comments? I don't know. Carlos, if you want to mention anything about the switch, if you've made any significant progress, or if we're just going to save that for the switch dev meeting.
Okay. But since next week won't be any meeting about the switch, but I have recently pushed like a command line interface tool just to launch some benchmarkings comparing the different architectures. So with this tool, you can like generate a traffic pattern, which is like just a TXT file or a CSV file, in which you indicate like the input and output port for a frame and its size. And you can fill this file with whatever amount of frames you want to send in any combination. So you can put like constant, like fixed size frames of constant size frames. So every frame with like a fixed size of 100 bytes, for example, or you can take them for a distribution. Now I have only used it like a uniform distribution. So you specify like the lower and the upper range of that, and you can get as many packets as you want. And also from you can parameter size it with the different radix and different data width for the bus width of the switch. And then you can just take this traffic pattern, load it into the simulation, and then I have used the stuff we commented in the other day in the switch meeting to obtain like each time, the starting time of each frame and the end time of each frame also, just to know the latency of each frame. And just I have made also a plot that I haven't pushed yet, but in which you can see like the different distribution, like an histogram, seeing the distribution of the latency of each of the implementation that we have. But now it's only the input queue switch and the input queue switch with the virtual APO queues, and we can see significantly the difference between them. So
That's
very cool. At least we are obtaining something. So
well, no, I mean, spending some time putting together some of this automated data collection and benchmarking stuff, that's great, because now once we get the some HDL put together for more finalized switch, we can compare it head to head against these kind of don't want to call them toy switches exactly, but that's kind of the idea. They're just for testing purposes. And we can make sure that things look reasonable. So you said you do see a difference between them, and that makes sense according to how they're supposed to work. So
of course.
That's
so
good.
with the built up queues, we get like you can see like the distribution of the latency is on the lower range of the latency instead of in the middle or as for the input queue. So we can see the differences.
Nice. Well, it'll be fun to start putting those plots up and see what people think about those, just to make sure everything looks reasonable. So I
was pretending to put them in the slides for the next switch meeting, because I don't know if maybe it's not the place to put it in the repository. So I don't know. Maybe we will wait for the next meeting. I don't know.
Yeah.
Or maybe I can put it then on the Zulip just to put something there.
You just go ahead and start. That's kind of the point with Zulip. You can just drop stuff in there whenever, and people can look at it. You don't have to wait for the meeting. As soon as you get results, okay, zup.
Okay. Yeah, for this moment it's very basic. So, but we can also extend it to whatever we want. Also for the bandwidth test and all the distributions of the traffic. So
well, I mean, basic is fine, right? You got to start somewhere, and then you start building complexity and whatnot on top of that. So sounds like you're making pretty good progress. I mean, I will say that maybe we will meet next week. It's just a question of, I got the jury duty on Monday. If I get put on a jury, then we probably won't be able to meet. But if I don't, which is probably what's going to happen, I mean, there's basically 3 potential possibilities, right? I go in there and I don't get called. That's happened before. It'll probably happen again. Number 2, I get called. I go in there. They go around talking to people. They're like, "So what is your occupation?" "Yeah, I'm a postdoctoral researcher." "Okay, cool. Thanks. Get out." Or the third possibility is I get put on a jury. And as that happened a couple of years ago as a PhD student, I got put on a civil case for a week and a half or 2 weeks or something like that. So so we'll see.
Yeah, if all the three possibilities have the same percentage of probability, maybe yeah, you are lucky and you can you have 2/3. So
Yeah, most likely I won't get called at all, but we'll see. Yeah. So anyway, depending on that, we can certainly discuss on Zulip, and if we want to meet, later in the week or something, we can certainly do that.
okay, great. Yeah, I just want to implement also the output queue version of also for this simple architecture. Yeah, and just try to plot the comparison of the three of them for some traffic patterns.
Right.
That's the
Okay.
main goal here.
All right. Okay. So you need to implement the output queued switch.
Yep.
Which you don't have that one implemented yet. Okay. And then I guess once all that looks reasonable, then we'll start chipping away at the hierarchical buffered crossbar.
Yeah,
Which
exactly.
is actually the one that we want to build. Okay. Well,
Exactly.
sounds like excellent progress.
Okay, thank you.
All right. So do we have any other questions or comments about anything? Okay. I guess if not, then I'll go ahead and, close things down then. Thanks everybody for tuning in to the meeting today. And as I announced at the beginning, I guess the next Switch Dev meeting will be on May 1st, and the next Corundum developer meeting will be on April 24th. So make sure you got that on your calendar. And I'll see you guys later.
Okay, see you. Thank you.
Thanks a lot, Alex. Bye.
Yeah, talk to you.
Thanks, see you. Bye.
Talk to you.